Okay, it's 10:30. You should be done by now. If you are not done with the evaluation, don't worry about it. You still have time till the 6th of July to do it. And yeah, for now, I would yeah, say, okay, we're done with that for now, and let's start with the lecture, with the actual lecture about the last file system we will talk about this summer. It's called Ext, ExtX. You will see what that means in a couple of minutes. I guess you can see the slides. Okay, awesome. Good. Okay. As always, you already know this book. You already know Brian Carrier. It's the basis for this lecture. Available on the internet. So in case you want to, get further information about Ext, for example, after today's lecture, you can refer to that book. You also already know Bloom's taxonomy. This is the general taxonomy. And what we want to learn today is how to define key terms and concepts of the Ext file system in your own words. You should be able to explain how Ext manages content and metadata in your own words after this lecture. We will learn about how to use forensic tools to extract and interpret Ext-specific information, how to reconstruct a deleted file. We will examine Ext structures, and after we talked about that, you should be able to detect hidden data or data hiding attempts, and you should be able to assess the forensic implications of Ext features like that's incorrect. Alternate data streams do not exist in Ext, but journaling does exist in Ext. So ignore that. It's a copy-paste mistake. Okay, let's start with the fundamentals and concepts. So the Ext file system is the standard file system of most Linux distributions. We are currently, or the currently used default file system is Ext4. Before that, there was way back before Ext4, there was the Unix file system, UFS. And Ext, all the Ext file systems are actually based on this Unix file system. So before Ext4, there was Ext3, Ext2, and as I said, UFS. And each iteration or each new version of the Ext file system added new features. For example, Ext3 added journaling to Ext2, Ext4 added larger file or larger volume support and larger file support. And so probably Ext5 will also introduce new features and will be able to maybe handle SSDs more efficient. We don't know yet, but the Unix file system was created to efficiently access data on HDDs. So they tried to keep the moving range of the magnetization arms as small as possible in order to make it more efficient. So that was the idea of UFS. So the idea of Ext5 could be to make SSD access more efficient. Okay, but I don't know. It's just like an idea. Okay, and as you may already know, Linux supports many file systems. You can also mount an NTFS or an FAT file system in Linux, but usually Windows is not able to read the Ext file system data contents. So if you want to create a data storage that you want to use with Windows and Linux, you should not use the ext file system, for example. Okay, but also in Linux, as there are many different Linux distributions, many different special Linux versions, homebrews, whatever. Yeah, each distribution is a little different, support different things. And but the good thing is usually as many Linux distributions support so many different file systems and versions of file systems and features, the user is free to decide which file system to use. But keep in mind that also not all Linux distributions, because there's such a variety, support every single feature of the different ext versions, for example. Okay, but something that is also important to note is that if you want to have a look at the carrier after this lecture in order to get more information about the ext file system, then you have to know that since the book is quite old, it only contains ext2 and 3 and not ext4. So this is why I tried to come up with that table you can see here, which should give you like an idea of the difference between ext2, ext3, and ext4. But yeah, as you can see here, ext3 adds stuff to ext2, ext4 adds some stuff to ext3, but the basic idea and the basic structure remains the same. So this is why we will mainly talk about ext3 today. ext4 supports something that is called extends, which is also known from other file systems like BTRFS. But it's like a more complex structure which has some advantages and disadvantages. But as I said, we will talk mainly about ext3 today. But there is a very good documentation of ext4 on the internet. If you Google it, you will very quickly find it. And also the Wikipedia entry of ext4 is pretty good. But the basic concepts, they remain the same. And yeah, as I said, ext4 is the current default of Linux, the most Linux distributions. Okay, so let's have a look at the layout. So extx is basically it's a very simple layout-wise, a very simple file system. There is a reserved area in the beginning, which stores all the file system data stuff, all the information about the file system. And then there are block groups, and the block groups, they store the actual file content. And I already told you that UFS was created to increase the speed and reliability on HDDs, and ext basically, adapts that and also aims to increase speed and reliability on HDDs. And this is why it is designed like that. Another interesting thing about ext is that the central data structures, which are stored in the reserved area, they are present in the file system multiple times, all with their speed and reliability in mind. So there are several backup copies of the most important data structures, and the data blocks for a file are also kept very close together or to each other in order to keep these paths of the magnetic arm, the read head, the write head short. I don't know why I do this weird thing with my arm when I talk about the arm and the head, but yeah, okay. I guess you know what I mean. Okay. So we will talk about all of that in detail in a minute. The other thing that is important in ext X3 or in X in general are inodes. Now that you already heard about FAT and NTFS, the inode is basically comparable with an MFT entry, for example, or in FAT there's not really something comparable, but maybe the FAT entries, they could be compared to inodes. So inodes are the main data structure that gives us information about files and directories. So here you can see an example where we have two directories, and in each directory there is one file. And each file and also a directory has an inode in the inode table, which gives us all the information about these things, so the metadata, and also where to search for the actual content. And yeah, so each inode has a fixed size and also yeah, an address, a number address, a unique numbered address. So yeah, each inode has like an address, a number, which can be used to find specific inodes in the inode table that belongs to specific files, for example. And the file name, this is the difference between, for example, an MFT entry and an inode. The file name or directory name is actually not stored in the inode. The names are stored in directory entries, which are comparable to the FAT directory entries. And each directory entry contains the name and a reference to the inode. Yeah, so this is how you can find all the metadata of a directory or file. You have to have the directory entry and the inode. Okay. Okay, and here you can see something also special for the ext file system, something that does not exist in NTFS and FAT. Here you can see that there are two files or two file names that point to one inode in the inode table and one group of metadata, and this is called a hard link. So we have one file with two file names, and one inode. So as I said, the file name is stored in directory entries. So this is depicted here. You have two directory entries which contain a name. Both of them have the reference to the same inode, and the inode contains the same data blocks. So the content is the same for these two files. We just have two file names. Okay, there are more additional functions or special features, maybe maybe that's a better name to call them. So, for example, all the ext file systems are open source file systems, so you could craft your own version of ext, basically. And there are several additional features that can be enabled or not enabled. For example, there are compatible features. As I said at the beginning, not all Linux distributions support all the features that are possible in the ext file system. So yeah, this is actually the compatible feature is actually a feature that can be used to use the file system even though not all features are supported by the operating system. Oh no, that's the incompatible feature. So with the incompatible feature, you can still use the file system, even though the operating system does not support all the features. Wait. No, the compatible feature does that, and the incompatible feature makes the file system not mountable in cases like that. For example, when compression is used, then the operating system that does not support the compression cannot use the file system, and because of that, it's not mounted. But in case we have like other features that are not supported, but do not restrict the usage of the file system as much as compression, we can still use the file system with our operating system, but without these specific features. And there are also read-only features. I mean, the name already tells us what it does. If an operating system does not support the read-only feature, the file system can still be used, but yeah, it's mounted read-only. Okay, so there are a couple of implications that arise with XX or XX for forensics. So the first one is that you always have to be careful with Linux in general, because Linux is such an open operating system. There's so much that you can configure or that you can specify in a very specific or special way. Also with the XX file system in general, it might be the case that the default Linux knowledge doesn't apply to very special crafted Linux distributions, for example. Yeah, maybe there's an own kernel extension or special file system functions that you are not aware of or that you wouldn't assume in a default Linux distribution. So there's always caution should be always given with Linux distributions in general. So for home users or commercial servers, the default settings can be assumed, emphasis on assumed. But for professional criminals, for example, they might craft something very special that is very difficult to analyze. Okay. Okay, as with the other file systems, we will now go through the 5 data categories of carrier or according to carrier for the ext file system, and we will start with the file system data. Can anybody tell me why we start with the file system data? And why you should also start with the file system data category when you analyze file systems. No one? Okay, somebody in the chat says to verify the original file system type, label metadata information in clusters. Yeah, almost. To check its integrity. Yeah, so verifying the file system type, for example, is a very good point. Also, how is our file system structured? So how big are our clusters? Like we have to verify the file system layout first in order to to draw conclusions later on, when we see something, for example, that makes us wonder, is everything correct? Does everything work correctly? Is this an inconsistency, or is this like regular file system behavior? In order to assess if everything seems normal or regular, we have to check out the file system data and the file system layout first. So this is what we do now. So I think I already told you about the reserved area a little bit. So the reserved area contains the file system data, and in the XX case, it contains a boot code. So the boot code does not necessarily has to be there, but in cases where the boot code is there, it's in the first sector. And after the boot code, we have a superblock. And the superblock contains configuration data. It does not contain boot code because in cases where we have a bootable file system, the boot code is in the first sector. By the way, the MBR from the partition table jumps to this boot code and then runs this boot code in order to, for example, start the operating system. Yeah, so by jumping from the MBR boot code to that boot code, yeah, we can directly load the operating system boot code stuff. Yeah, as I said, only in cases where the file system or the partition, the medium, the volume is bootable. So the superblock doesn't contain any boot code, but configuration data for the file system. And the superblock is 1024 bytes in size, but many of these bytes are unused. It contains, for example, the size of a file system block. So with Ext, we talk about blocks, not clusters. And it gives us information about the total number of blocks in the file system, the number of blocks per block group. We will come to that in a second. And the number of reserved blocks before the first block group. So the size of the reserved area, and the starting of the block groups. And yeah. And after the superblock, we have something that is called group descriptor table. It contains a group descriptor entry for every single block group. And this is also something that does not necessarily have to be there. It's usually there in cases where the superblock isn't sparse. And in the block groups themselves, there is another group descriptor table, which is a copy of that group descriptor table, which also contains the group descriptor entry for the block groups. And block groups are, yeah, a number of blocks. So Ext stores everything. The content, all the content data is stored in these block groups, and this is basically where the block group area starts, if you want to call it like that, or content areas, data area starts. But the data area is separated into these block groups, and each block group contains a group descriptor, which is yeah, an area in the beginning of each block, and each block group is basically like a small mini file system in the file system. The group descriptor stores, for example, a backup superblock. It also stores the backup group descriptor table that we just talked about. It also stores a block bitmap, which gives us the allocation status for each block in the block group, and an inode bitmap, which gives us the allocation status of each inode for the blocks in the block group. And then there you have the inode table for this block group. And yeah, as I said, this group descriptor table contains a group descriptor entry for itself then, because yeah, so here in the beginning you have the group descriptor table which contains an entry for each block. And now that we are in the block itself and the group descriptor for this block group itself, it has to contain a group descriptor entry for itself. Does that make sense? Are you good so far? Are there any questions? Everything all right so far? Okay. Okay, let me check my notes. I think I told you everything. Yeah, I think I did. And the blocks, they actually store the content of the files and the directories. And if you analyze a block group, for example, with the SleuthKit, then the output can look something like that. Here you can see the block range. In this example, we have 0 to whatever X blocks. The block size is 4069 bytes. We have several free blocks left in the file system. We have 118 block groups and 32,000 something blocks per block group. So you can see the block groups, they do not contain like 4 blocks or something like that, but a high number of blocks per group. And this is why I said it's like a mini file system in the file system, because each block group manages a larger number of block groups with their own mini file system data. And here you can see how many inodes per group we have. And this is the output for group 0. There you can see the layout of the block group. The backup super block is in block 0. The group descriptor table is in block 1, data bitmap 2, inode bitmap 3, inode table 4 to 512, and then we have data blocks from 513 till the end of the block group. And we have many free inodes here, no free blocks actually, and 11 directories. So this is how the SleuthKit output, for example, looks like for such a block group. Okay, in cases where we have to analyze the file system data, then we have to analyze the super block and the group descriptor table in order to get information about the layout of the file system. So for example, this answers questions like where are the individual block groups located. This is something that is or can be found in the super block. We can answer the question where are the inode index nodes or the inodes of the files located. In cases during this analyzation, we should also keep an eye out for data that is hidden in certain locations. For example, I told you that there are lots of free bytes in the superblock where people could hide data, and of course also in the superblock copies. The boot code is usually unused So, or the space for the boot code is usually unused. So there could be data hidden. And as always, we have file system slack and volume slack. And yeah, in cases where the superblock is corrupted, then you have to keep an eye out for a backup. And you could do that by searching for certain values. Yeah, so in cases where the superblock in the reserved area is corrupted or not there for some reason, of course you cannot look for the block groups, but you can look for specific values in order to find a copy. Okay, then let's continue with the content data in cases you don't have any questions. Okay. So content data refers to the actual content of files and directories. And as I said, the content is stored in the blocks, in the block groups. And to define a couple of terms, first, a file system or a data block in ext3 is a sequence of continuous sectors on the disks. How many sectors is up for configuration in the superblock, so there are several sizes possible, and as I said, the exact size is specified in the superblock. All blocks have logical file system addresses, so the blocks in the block group start with 0. We also saw that in that example output, that in this block group we start with block 0. Yeah, and almost all blocks belong to a block group. There is an exception, for example, the block before the first superblock, and the reserved blocks directly after it. So the reserved area doesn't belong to any block group, which makes sense, I guess. And yeah, important to note is that the allocation status of blocks can be read out in the block bitmap. We already talked about that. And the block bitmap is exactly one block in size. So with 4096 bytes per block, each block group therefore has a maximum of 32,000 something blocks. Okay, and as with NTFS and FAT, we have to talk about the allocation of blocks. I told you before that the allocation strategies or the allocation algorithm is dependent on the operating system and the driver implementation. But there are things that can be assumed, so usual behavior, and usual behavior is, if possible, new blocks are always allocated within the same block group. So this is usual behavior. This is something that you can assume that happens. And space for new blocks is searched from the start of the block group. Of course, it makes sense. And space for enlarging files is sought directly behind the file, which also makes sense because we talked about it before. So blocks, so in X, blocks are tried to kept together, or their file system tries to not have distance between the blocks because of the speed and reliability goal behind the X file system. Okay, and only when the block group is full, then other blocks from other block groups are used, and how this is done depends on the operating system. and the driver. And there is a number of blocks that are reserved for a specific user. So, for example, for which specific user, I don't have a good example now, but the number of these reserved blocks can be found in this super block. And it's these special reserved blocks are for the root user. And another interesting thing is that Linux writes zeros to the entire block before it writes content to a block. So this means for us that there is no slack space in data blocks. So we cannot find residual data from a usage before or from files that have been allocated to that block before. So Linux and the combination of Linux and ext is one of these combinations where you cannot find any slack space, which is, for example, not true for NTFS and FAT. Okay, so in order to analyze content data or in order to answer specific questions about content data, for example, how do I find out whether a particular block is occupied, we have to do or process certain steps. We first have to find out which block group the block belongs to. Then we can check out the block bitmap and then find the bit that represents the allocation status for that block. And then we have the block status, or that's how we can find out if a certain block is allocated or not. In cases where we want to find out which blocks are currently not allocated, we could basically do this thing. We go through every single block group, check out the bitmap and see the allocation status, and then we know which blocks are currently not in use. And what do I want to say with that statement? I don't know anymore. Give me a second. Okay. So the question is, how can we find information about the allocation status of the superblock, the group descriptor, table, and the boot code? Does anybody has an idea? How can we figure out the allocation status of these special locations? No one has any idea. So are these special data areas or data structures, are they in any block group? What do you think? Come on, guys. Are they in any block group? We talked about it a couple of minutes ago. No, exactly. They are not in any block group. And this also means that there is no such thing as a block bitmap for these data structures. So we cannot check out the allocation status of these data structures we also don't have to, because they are special data structures. So in cases the file system functions in a regular, normal way, of course the superblock is allocated because it's the superblock. Also the group descriptor table. The boot code is something different. I told you about that. The boot code does exist if the medium is bootable, but in cases where it is not bootable, there is no boot code. So yeah, we actually do not really care about the boot code in ext3 because it doesn't contain any data that we need to analyze, for example, the file system layout. Of course, boot code viruses can be there, but in cases where the boot code area is empty, yeah, it's empty. It's not allocated. So that's that. Okay, 3 more points regarding content data. We have, as I said, we have several allocation strategies, and yeah, so because of the usual allocation strategy that we can assume to be in place, the search for deleted file contents can usually be limited to the block group. So in case where we try to find a deleted file or the contents of a deleted file, we usually only have to search in one specific block group and not several block groups. But it could be the case that contents can be fragmented over several block groups, which is usually usually the file system does not do that because of the speed and reliability thing. And in FAT and NTFS, each cluster had almost the same probability of being written. In ext, it depends on which block group a block is in. Okay, are there any questions? What are superblocks again? So the superblock is the main data structure in the reserved area that gives us the information about the file system layout. So how many blocks do we have? How big are the blocks? How many blocks do we have per block group? Like all the information about the file system itself is stored in the superblock in the reserved area, and there are several copies of the superblock in each block group descriptor. Okay. In cases there are no more questions about content data and file system data, we will now continue with metadata. And I already told you that all the metadata all the metadata is located in inodes. I was about to say except of the file name, but the file name data is an own category. So the metadata is stored in inodes. Each file and directory has an inode. Inodes usually, I told you they have a unique number and unique address. Usually inodes start with number 1. And 1 to 10 in the inode table are reserved. They are usually not all of them are occupied usually, or they are always occupied, but not all of them are actually used. There are a couple of reserved inodes that are used for particular data structures. For example, inode 2 belongs to the root directory. Inode 1 usually collects damaged blocks, but we already talked about damaged blocks before. So damaged blocks or bad blocks are usually handled by the storage device nowadays. So you shouldn't have many damaged or bad blocks in your file system. Inode 8 is usually reserved or belongs to the file system journal. And then we have 11, and 11 belongs to the directory lost and found, which collects occupied index nodes during the file system check to which no directory entry points. So we have inodes with metadata, but we don't have any file names that belong to these inodes. So in the lost and found directory, you can find metadata for files where you don't have a file name. Okay, and yeah, we already talked about that. Inode bitmap gives you the allocation status of each inode. Okay, what's the content of an inode? Usually we will find information like the file size in an inode or the owner of an file or directory. The owner can be a user and a group ID. And the ID doesn't have to be assigned to anyone and can easily be changed using chown. You should all know this command, I guess. Yeah, so we have file size owner. Of course, we also have timestamps, and in XX we have data in seconds since January 1st, 1970. So this time is usually called the Unix time in UTC, and every timestamp is stored as seconds since this date. And I think, I mean, it's probably it's not really important, and probably every single person has a different opinion on that. But I think this timestamp does make more sense than the NTFS timestamp or baseline timestamp, which is used to give the seconds since. Okay, this is confusing. So in NTFS, we also have a certain timestamp that is used in order to give you the seconds since that timestamp as a timestamp. And does anyone remember what date it was? So for for XX, we have January 1st, 1970. But what do we have for NTFS again? Does not have to be like super correct, but ish. Does anyone remember? Yeah, exactly. It was 60, 100 something, yeah. So a time period where a computer didn't exist yet. But 1970 makes more sense, probably. Okay, anyways, we have certain timestamps like the last access timestamp, last changed to the content of the file, last changed to the file's metadata. We have a file stamp in cases where files were deleted, which gives us the date when the deletion occurred. And we also have a timestamp for manipulation by, for example, touch. So many timestamps that we have here in XX. What else do we have? We have a mode a field that gives us information about what kind of data we have here. For example, we can have a file or directory. So I told you before, every single file and directory has an inode entry. So it gives us information about whether it is in file or directory. It can also be some kind of other file. There are several file types possible in XX. But the most important ones are files and directories. And we also have a reference counter, which tells us how many directory entries point to this index node. And an index node is only deleted in cases where the reference counter reaches 0. So if that happens, then this index node is deleted. And of course, we also have references to the data blocks. And the references to the blocks can, there are 3 types of references that we can have. So consider this example. We have a directory entry which gives us the name of a file, which is called file1, and a reference to an inode. And then we have our inode table here with this inode for file1, which contains timestamps, for example. Sorry, I forgot to translate that. And then we have the references to the blocks. And as I said, we can have 3 types of references, but actually we can have 4. I forgot one important, an important one. We can have a single direct reference, which directly points to a data block. We can have a single indirect ones, which points to a data block, and that data block points to another data block. We can have a double indirect reference, then it points to a data block, which points to a data block, which points to a data block. And we can have triple indirect reference pointers, and they point to a data block, to a data block, to a data block, to a data block. And we can have 12 single direct ones. We can have 1 single indirect one. We can have 1 double indirect one, and we can have 1 triple indirect one. Yeah. So this is how we can reference blocks for inodes, and these pointers actually also give us the maximum possible size of a file. Okay, what else can we have in EXTX? We can have attributes. And these attributes, they work similar as the attributes in NTFS. We can have, for example, an attribute that tells us that this is an immutable file which can no longer be changed, or that we have an append-only file, an access control list. The attributes that are possible, they depend on the operating system. So the different Linux distribution, they support different attributes. So in NTFS, the attributes, they contain like very basic information about the files. For example, we have a standard information attribute, which gives us timestamps. We have a file name attribute, which gives us the file name. We have the data attribute that contains the actual file content or cluster run list. And in EXTX, the attributes give us additional features or additional information about the files or directories. So not basic information, but additional information. And as with the file content, we also have to think about the allocation status for metadata. And there are several assignment strategies dependent on the Linux distribution that is used with the file system. And for example, this strategy is in Fedora Core 2 example. So it's an older version of the Fedora Core, but as I said, it just serves as an example. So in this case, for new file, new space, for the index node or the inode is allocated initially in the same block group of the parent directory. And if this is full, another block group is searched for using square hashing. And for a new directory, a block group is searched for that has been little used up. Has been little used up to now, and the statistical data on how used a block group currently is can be found in the group descriptor, and the first below average block group is then selected for a new directory. And in case an entry shall be deleted, ext3 and ext4, they set the file size to 0 and delete references in the inode. Also, the indirect block references are deleted, and ext2 does not delete this value. So in the case of ext2, a recovery of deleted file content is still possible because we still have these references. But in the case of ext3 and ext4, it's not possible anymore. Okay, in order to analyze metadata, we always have to find the index node or the inode of the file. Then we can search through, or in order to do that, we can search through all occupied or unoccupied inodes. We can use the inode bitmap for that. Then we can read out the inodes for allocated files, for example. Timestamps gives us information about when a file was deleted, for example, and the actual file content recovery is dependent on the version, the XX version, and as I just said, for ext2 it's easily possible, for ext3 and 4 it's not that easy, and in cases like that we can still use file carving, for example. Okay, any questions about metadata? Okay, if not, we will continue with file name data. I already told you that file names are stored in directory entries, and directory entries are located in the data blocks of the directories. So it's very similar to FAT. They contain the file name and a reference to the inode, and each directory begins with the entry for the current directory and the parent directory. Let me check my notes. Yeah, the directory entries, they basically form a list or a table, and the information about how long a file name actually is and where the next entry begins is also contained in the directory entry. And so let's check out this example. We have a directory entry here, like this is the list or the table. Yeah, list is probably a better word. And we have several entries in this directory entry list. And as I told you, it always begins with the current directory and the parent directory. So the name of that directory is dot, and we have a reference to a certain block. And then we have a pointer to the next entry, which is dot dot, and the reference again. Then we have a pointer to the next entry, and so on. And when the next pointer is, or when a file is deleted or an entry is deleted, the next pointer is simply moved to the next entry in the list. And the file name remains unchanged. Yeah, just the next pointer is moved to the next entry. So with the help of these pointers, you can always find the next entry in the list or the next valid entry in the list. Yeah. Let me check out my notes. Yeah, and because the next pointer is simply moved to another entry in the list, there is a chance that an old entry can still be found in the directory entry list or the block that belongs to a directory. There can also be slack space. You can call it slack space if you want to call it like that. But yeah, this residual data from these directory entry can still be there sometimes. So sometimes it's possible to restore file name data in the directory entry list. Okay. We already talked very briefly about hard links. A directory entry is also called a hard link. Yeah, so let me check out that slide very quickly. Yeah, so the directory entry or the hard link is a direct link to the inode. The directory entry contains the name and the reference to the inode. So it's a direct link to the inode. And I told you before that there can be several of those hard links to the same file. So the same file can exist under several names. And the file is only deleted certainly deleted when the last hard link has also disappeared. And so, for example, dot and dot dot, so the current and the parent directory are hard links to the current and parent directory. And files can also be marked as soft links. In these cases, the data content contains file names to which the soft link refers, and this is useful for links to other file systems, for example. So soft links also work across file systems. Okay, so if you consider that example, we have a file which is stored under the name file1.txt, and there is a hard link, a second hard link for the same file, and the name for that hard link or the second name of that file is file2.txt, for example. And then we can have an additional soft link txt to that file again, which can be used to have a link that works in several file systems. Okay, that's basically it. Okay, if a new directory entry is created, Linux searches for the beginning of the directory for free space for the entry. And if no space is found, the file name is added to the end of the directory. And if free space is found, then of course the directory entry and the name is stored there. And directories are usually not defragmented. Yeah, but fragmentation, we talked about that, is also nothing that you have to worry about anymore, actually. Yeah. You do not have to worry too much about it. Okay, in cases where we want to analyze directory structures and directory entries, we have to start to search for the root directory. And I told you before, the root directory has a reserved inode, which is inode 2. And so via inode 2, you can find the root directory, and from the root directory, you can traverse the directory hierarchy and search for all the other directories. If you want to search for deleted file names, you could go through the entire directory and all the directory entries and look for spaces between the file names in order to find residual data of file names that have been deleted in the past. And yeah, an entry with a short file name will probably exist longer after a deletion than a long file name, because the bigger the longer the file name, then the bigger the space, and it's more likely that this bigger space is reused faster than a very small entry, for example. Okay, and of course, data can also be hidden in unused directory entries. Yeah. So that's it for metadata. The last category that we are currently missing is application data. And application data, I told you before, mainly refers to journaling. And X is actually a file system. X3 and X4 is actually a file system that has a journaling function. We can find the file system journal by analyzing inode 8. And it's a very common feature today to have a file system journal. As I said, it's implemented in X3 and 4. In X2, I think we don't have it. Yeah, and the journal actually logs file system actions, and it performs updates in the form of transactions. So these updates, they should be performed on blocks, so it logs whether how blocks are used, and yeah, so basically everything that happens in a file system, the journal logs, and how the blocks are used is being logged, and yeah, the journal is regularly updated. So if you want to learn more about journals, I think you can have a look in Carrier's book, at least for the X3 journal function. Yeah, so there's actually not much to say about journals here. So let's, before we don't have any time left, let me very quickly summarize what we learned today about Ext. I think this example from your book summarizes all these structures in a very nice way by looking at a file allocation example. We also did it before with FAT and NTFS, but this time I basically just ripped it off the Carrier book. Yeah, so let's have a look at that example for file allocation. So in case we want to allocate a file, or in case a file is allocated, the first thing that happens is the superblock data structure is read, which is again 1024 bytes in size and located 1024 bytes into the file system. So the boot code is 1024 bytes and the superblock also is. And from processing this, we learned that the block and fragment size in this example is 1024 bytes. So let us check out that step. We're currently here. Each block group in this example has a certain number of blocks and inodes. There are no reserved blocks in this example before the start of the first block group. Then the second thing we have to do is we read the group descriptor table, which comes after the super block. Yeah, this tells us something about the layout of each block group. Now we have to locate the directory where we want to put in our new file. So in order to do that, we have to search for the root directory. So we have to process inode2. So where we are now, we have two block groups here, block group 0 and block group 2. So we go into block group 0, where the directory is located that we want to put a new file in. So we process inode2 in this inode table, find the root directory of this block group, which is block group 0. This is why it is the root directory. And we find directory number 1 here. Okay, and so in order to locate the directory number 1 in the root directory, as I said, we have to process inode2, and with the number of inodes per group, we determine that inode2 is in block group 0, which is usually the case, or which is the default case, and we use the group descriptor table entry of group 0 to determine the inode table, the location of the inode table that starts in block 6 for that group. So we now found the root directory. We can find directory number 1 by that. I try to shorten it down a little bit. Okay, as I said in the beginning, the first two entries are always the current and the parent directory. So now that we went through the root directory and found directory number 1, we can see here that we have an inode reference for that directory, and this inode is located in block group number 2, in the inode table of block group number 2. And from that, we know that the content of dir1 can be found in that block. And the content of a directory is actually the directory entry table. And from there, we read the directory entry table contents and process the contents as a list of directory entries. We are looking for an unused space in the directory where we can put our file name in it. So in this example, the file name is file1.dat. So we add the file name in this case, between two allocated directory entries, 12.jpg and 14.jpg. There we put our new file name in. Then we have to assign it an inode, and in the inode we assign it blocks in the same block group. And yeah, then we can write our file 1.dat contents to these blocks. And now our allocation for that file is basically done. Let me check if I forgot something. Yeah, no. we did everything we have to do. Of course, then all the other structures are updated. For example, the group descriptor table after the superblock is updated. Also, the information about the free blocks count in the superblock is updated. All the time stamps are updated. And the bitmap changes. We have an entry in the journal because we allocated a new file, and that's it. Now our file is allocated and all the structures are updated. Okay, I'm running out of time again, so let's quickly talk about what happens when we delete a file. When we delete a file, again, we have to read the superblock. We have to read the group descriptor table. We have to process the root directory, find the directory in which we want to delete our file. So now we want to delete file 1.dat that we just currently created, or that we just created a few seconds ago. So we basically have to do the same thing: superblock, group descriptor table, root directory, dir number 1, find the contents of dir number 1, change the next pointer in the directory entries from 12.jpg to file 1.dat to 14.jpg. And give me a second. Yeah, then the inode has to be processed. The block reference are zeroed in the inode. The file content is still there, so we can still carve it, but all the block references are deleted or zeroed out. We again update the block bitmap, the inode bitmap, the group descriptor table, and the superblock. Journal entry is created. Yeah, the timestamps are updated, and that's it. Now our file is deleted. And that's it for ext. I'm a little late again, but only 2 minutes today. I hope you understood